All right.
Welcome to Nested Loop, session 4. We're going to wrap up chapter 3, last 3 pages there, and move on to chapter 4.
That sounds like a plan.
So I'll turn it over to Andrew to finish up his. I'm going to go pull up the Kindle version of it.
Yep.
And Andrew wants to share his version.
All right.
With that.
So I'm just going to start from this section, choosing dependency direction, and just kind of go through it pretty quickly. Just the definitions for abstract and concrete classes. So when we talk about this kind of spectrum between abstract and concrete, we're looking more at what or maybe how much a class changes, and we qualify that by saying that a class is either concrete if it changes fairly in a fairly quick sense, and an abstract class is something that's stable in a sense. It's more like it's really difficult for me to just give like a great definition, because I feel like these are more like a feel, it's like a diameter. This we were dealing with a wheel class, which is a very concrete class. It's something that describes an object, and it's bound to change, given that people can want different requirements for a wheel. We saw that in this chapter, we went from using the wheel object to finally calling a diameter method that then was an interface that our code used. And so now we're no longer dependent on that concrete class, and we were more dependent on something that was abstract, like an interface. So in using that example, the idea is we're able to say, a diameter is straightforward. It makes a very simple statement. A wheel can be much more complex and could have different interpretations, which could mean different requirements, which would mean more likely to change. I'll kind of breeze through these. The examples that Sandy was using was that a framework class, let's say Rails, is more likely to change than, let's say, the Ruby base classes like string or array. Very, very practical. Almost everyone has dealt with strings and arrays and knows that they respond to very similar methods. And in that sense, most of our code, not all of our code, depends on these very basic fundamental classes, these abstract classes, because they don't change. And so by definition of abstract, we know that these classes don't change. So that leads to the next portion of using concrete and abstract classes. When we use classes, in our code, we call those dependencies, where our code is now dependent on those classes to respond to methods or to, well, let's just say we use methods from those classes. The point that Sandy wants us to understand in this final section, is that we want to go from using concrete dependencies to abstract dependencies. And we can see that in this chart here. We have 4 zones: the abstract zone.
Are you intending to share your screen? Because you just
I'm sorry. I thought I was sharing the entire time. I got confused with Chromecast. Sorry about that, guys. Here we go. Almost there. All right. So we're here looking at the 4 zones: the abstract zone, the danger zone, and the neutral zones. Essentially, the way I understand it, dependencies are not a big deal if our classes, let's say we have several classes that are abstract interfaces or just abstract classes. As far as dependency directions, we're okay. We can have many dependencies or we can have very few dependencies for those abstract classes. Where it becomes a problem is that we have concrete classes. Now, if we have concrete classes, we want to manage those dependencies, and we want to see that our concrete classes have very few dependencies. Reasons being, since concrete classes are by definition classes that change frequently or are more likely to change, those other classes that depend on that concrete class will be more likely to break and thus require debugging. So anything that we can do to mitigate that, to take a concrete class out of the danger zone and into the neutral zone, might involve, making more abstractions, something that we were doing before in the chapter. We go through in detail examination that N3ST3DLOOPS gives us, given us that in zone A we have an abstract class that has many dependencies, and she calls it the abstract zone, meaning that it's a class that's used by many other classes, but that offer no dangers as far as code stability.
No, it depends on other classes.
Dependencies?
Yeah, it has many dependencies. Not many classes depends on it. The class depends on many other classes. That's because this class doesn't change. It's fine.
Okay. I got my directions mixed up. It's number of dependents, right? Can we get some feedback from everyone else? Are we talking about dependents or dependencies?
Dependents.
So that means other classes depend on it. On the abstract class, in this case. So let's say I have the class string. It's an abstract class.
Well, maybe I'm reading the wrong way. I think the number of dependents is how many dependents.
It's kind of like the child classes, like
dependent. People depend on it. Many people use string.
Okay.
So many people are dependent on string.
All right. So sorry, I misread.
Right. And if string breaks, then everyone's code changes.
Yeah. Yeah. So it's like, I don't even know. I don't have a good example for that, but
string.
Yeah. So I don't know how a string would break. But if it did, like it starts.
Like if suddenly someone decided length wasn't the size of string in bytes, but I don't know, number of syllables or something, right? And everyone's code suddenly breaks. I mean, you wouldn't make such a change, and also that's why string doesn't change, because string is a well-defined thing.
Yes. But
it sits at the point where many people depend on it, and arguably it could be an abstract class. String happens to be a concrete class, but you can have subclasses of strings, safe string, I don't know, censored string, something like that. That would be subclasses. But yes, living in that zone suggests that maybe it should be abstract, especially if you're writing your own classes.
Abstract classes, for the most part, can have many dependents or few dependents. I would say they're both abstract zones, but for this case, she says it's neutral when it's few. I guess it's an easier way of just keeping it in mind that there's just one abstract zone. On the right side of that chart, that's zone D and C, is known as the danger zone when the concrete class has many dependents. meaning that something that's just, we can say wheel, again, wheel might change. It might say we're no longer looking at a wheel that responds to, how do I say it? We no longer make a new wheel by doing, a previous call. Now that changed because we have new requirements, and those requirements now require the color of the tire. And so now when any of the dependents calls,
rubber.
yeah, the type of rubber. And so now when any of the dependents call a new wheel, it breaks, given that wheel changed. So it's a class that, because it's I guess it's more open to interpretation. If we look at string, we can't really say, oh, a string, yeah, I want it to respond this way. I want it to give me only strings that rhyme. I don't know if that makes sense. So, but no one would make that sort of implementation. So that change would be less obvious. Well, yeah, I shouldn't talk in absolutes. Maybe there'll be, some language where string would change often. It's zone C, even though it's concrete, if it has a few dependents. So if we were sure that we were in total control of wheel and what was calling wheel, that it was all right to have other classes call it, since then that number was managed. That number of classes that depend on it was managed. And so anytime that wheel changed, it was easy to implement those changes in other classes. So what does this mean for us? This means that coding is a very contextual based exercise where context is key. As soon as we start making public classes, as soon as we start making these classes available to other users, it's recommended to move concrete classes to abstractions so that there's less hassle. I'm not saying that has to be done for every concrete class. It's easier to maintain stability and user approval of a class.
Well, there's a couple of things that could be extracted out of this. Mm-hmm. One, like they say, yes, it's also, now we're talking also about design, right?
Yeah.
And it's pretty much these 4 corners or 4 quadrants. What they're trying to explain is that you have to keep in consideration the likelihood of change, which means there is a recognition the requirements will change. The code evolves. And as you as a coder needs to recognize those areas that are more likely to evolve, the areas that are more likely to not evolve and change, and make then those abstractions. To separate the thing that will change from the thing that will not change. The thing will not change become abstraction. The thing that will change become concrete, something that are likely to evolve. So you minimize the effects of one versus the other. Mm-hmm. Like the tire. In the beginning, we were talking about bike tire, but now this class is so good, we want to use it for car tires. And now you gotta create a different thing. How you build a car tire versus bike tire, it's a definitely different process. You gotta it's not just about diameter, it's how the width of the tire, all those kind of things. Now you're gonna separate what makes a tire versus a specific tire, mm-hmm. Right? Those are the kind of example that you were looking for.
Yeah, where the idea is recognizing that something has become more concrete, and then doing, as Diego says, trying to remove those abstract portions, and so that it almost quarantines that concrete ness of a class. I guess it's a good idea, almost like quarantine. It gives the idea that you don't want it coming into contact with the rest of the population, in a sense, and to mitigate the risk. So in summary,
yeah, real quick on this one. So if you remember last time, we were looking at how Sandy was trying to isolate creation of wheel and access, even down to the point where she wrote a method diameter that turns around and calls wheel.diameter. And so in doing that, if the class only calls its own methods, then if the wheel interface changes, it's isolated in the creation and that the delegator to diameter. So you can call your own methods without changing those because you just change it in two places. So while it's not extracting a class, I guess she's predicting that wheel will change. So the way she isolates it in her code, where now I don't explicitly pass parameters to wheel in more than one places, and now I don't even call the wheel object directly. I have a method called diameter that calls wheel.diameter. And wheel itself turns around and calls at wheel. And so she's isolating that. So if wheel changes, the rest of the code only calls the own methods in the class. So when that quadrant where, yes, changes can happen, but they don't affect a lot. Well, you can go back and change or adapt or however you need to in those two methods. Let's say diameter is called in 20 places. Well, I just change the diameter on that class if I had to change something. Like maybe it took in a parameter when it didn't used to be before. I don't have to change it in 100 places. I only change it in one place. So it's still that. There's a saying like you can solve all problems in software with another level of indirection. In this case, it's two methods, but it could be another class, which the method turns around and calls that.
That inclusion of that method is like an abstract interface where gear is a concrete class, but doesn't really depend on wheel anymore. Although it does have a method that calls it, it now kind of pushes it in within a method. All right. Okay. Any other thoughts? Should I go into summary? All right. So in summary, we've seen that we've reviewed dependencies and we've tried to do different refactoring styles where we've gone and we've injected dependencies so that we're no longer calling out a dependency within a method we have now set as an instance variable, which is called only once. Or in the case that POODR mentioned, we've isolated a dependency so that if it does change, if it's concrete, it only occurs in one method, thus allowing us to debug and fix it in an orderly manner. And then finally, we've looked at managing the direction of dependencies with our code and classes that we create. Thus, in the future, not future-proofing it, but just making it more manageable. We're not dealing with, it's not spaghetti code either. It's just, it's more like nested bombs or something where it's just bound to like explode. And so if we have less of those, it's a better workflow. And that's my presentation on chapter 3. Thank you.
My comment on it is I personally like the fact that she talks about different types of dependencies, like method dependency, argument dependency, and not just class dependency. Ken Beck in one of his books talks about it. Yeah, something that You have to keep a track of, okay, when you create a new method, how much the user of this method needs to know.
Yeah. It's worth noting that dependency injection is a much bigger topic in Java because of static typing. We get away with a lot of things, and we're not going to say get away. We don't have as many hurdles to overcome between duck typing and metaprogramming. You can think about the kinds of magic that RSpec does. It's like, oh, well, we can do things. We can inject things without, in a way that's less involved. I mean, Spring, for example, the whole framework to handle dependency injection. And there's other ones for that one. So pluses and minuses. With strict things like that, you get compiler checks, the errors you might make. But on the other hand, you have to put much more boilerplate plate stuff to do stuff. So plus or minuses.
Yeah, I think when you work with stuff like Java, you have because of the, you have to say which interface this object is going to be or support.
Mm-hmm.
You have to think a lot more about interfaces.
Yeah.
And that's a good and bad, because you end up, quite often, you end up finding code that either has one gigantic interface that every class implements. And so when you need a new method, you add it to the interface, and then you have to add the implementation to all the classes that have an interface.
Mm-hmm.
Or you have like a lot of small interfaces, and when you change one, you have to find out those classes that have their one interface. And so like you kind of deal with the same type of granularity, but the fact that you still have to go and hunt them down, it's a little bit of pain with Java. Now, one other thing is it forces you to think about interfaces a little bit more, which it can be a good thing.
All right, cool. So we're going to switch gears. Alex is going to pick up chapter 4.
Yes.
I want to switch and share his
That is what
ebook reader type thing.
Yep.
Go.
Just trying to figure out how to share this. Looks like I'll have to do this.
And swing it, the cursor to the left, and the sidebar menu comes the green rectangle.
Okay, so let's do this. And I'm using a free trial testing this out, so let me get rid of this. All right, everyone can see this?
Yes.
All right.
I'm excited you made slides.
Yeah. We'll see how they actually are. So, practical object-oriented design in Ruby, chapter 4, creating flexible interfaces. So this is a quote straight from the book that I thought was a good quote for this chapter. It says, domain objects are easy to find, but they are not at the design center of your application. They are a trap for the unwary. If you fixate on domain objects, you will tend to coerce behavior onto them. Design experts notice domain objects without concentrating on them. They focus not on these objects, but on the messages that pass between them. So I thought that was important because this whole chapter is sort of about how your application is made up of the sum of your messages, and not necessarily just your objects. So let's defining interfaces. An object interface is like a kitchen interface. So customers will order food and communicate with the kitchen through the menu. The menu is the kitchen's interface, right? So the customer knows what they want, and they don't need to know how it was made. And the kitchen only has to expose its public interface, which is the menu, and it can hide its internal interface, so customers can't go into the kitchen and mess around, hopefully. Right? That would be bad if customers were allowed to. So pretty much we're relating kitchens to objects here, right? In that, your public interfaces should only be what a menu is to a kitchen. You know, so you should be able to pretty much your public interface should hide away all of its internal workings, right? And it should only be. I'm trying to figure out a good way to say this. It should only. Oh, see, got that too far. It should pretty much. It should only expose what is what's needed, right? So this is too many cooks here. I thought that would be a funny GIF for here. If you guys have not seen the Adult Swim, Too Many Cooks, and have 11 minutes to spare today, I suggest you watch it. So the methods that make up your public interface, of your class comprise the face of it presents the world. They reveal its primary responsibility, are expected to be invoked by others, and they won't change on a whim, are safe for others to depend on, and are thoroughly documented in the tests. Whereas, and here I have a picture of the menu, whereas private interfaces, right, are all other methods in the class are part of its private interface when they handle implementation details, are not expected to be sent by other objects, can change for any reason whatsoever, and are unsafe for others to depend on, and may not even be referenced in the test. So, you know, that's more of our kitchen in this analogy. Am I moving at an okay pace? Am I moving too fast?
I'm good with it.
Okay, cool.
I do like that she has these rules. The key, I think, the key thing is better in the private, where it's unsafe for others to depend on or for change for any reason whatsoever. Because sometimes I often find I want access to private methods. And I realize, well, some of the methods that are private, like when you do the first part that they're saying are expected to be evoked by others, that expectation may be different between the creator and the users. So I think the rules in private which say, hey, can change for any reason.
Right. That's
probably the ones you should make private. And a lot of people do in Ruby, they don't bother with private at all. And even Ron Jeffries of Extreme Programming fame made some comment about private's not that much of a deal, but on the other hand, he's been coding for like 50 years. So, with a lot of time in small talk. So he probably has a better sense of how to break his methods up and say, many of us do.
Right.
But I kind of like that criteria. Oh, anything that's unsafe for others to depend on, make those private. That sounds like a good criteria.
Yeah, and it was it's definitely interesting seeing. I guess I never thought of the rules of what would make public versus private. So it was nice to see it broken down in obviously a general way, but yeah. Okay, finding the public interface is the next section. And this is a quote from the book. The design goal, as always, is to retain maximum future flexibility while writing only enough code to meet today's requirements. Good public interfaces reduce the cost of unanticipated change. Bad public interfaces raise it. So one thing I thought that was important from this chapter was, or from this section in this chapter, was asking for what instead of telling how. So you don't send messages because you have objects. You have objects because you send messages, right? So the distinction between a message that asks for what the sender wants and a message that tells the receiver how to behave, it may seem subtle, but the consequences are huge, are big, right? So interface communication is much more desired. Something like, I know what you want, and I trust you to do your part when communicating with the object. She talks a lot about blind trust being important in object-oriented design. So pretty much, being able to trust another object that it's doing what you imagine it. So it allows objects to collaborate without binding themselves to context. and is necessary in application that expects to grow and change. Oh, hold on. I think I'm missing a slide in there. Okay. I'm not. Maybe not. Okay. Well, it goes on further. It has this section on creating explicit interfaces, which I thought was interesting. This is a quote from here. Every time you create a class and declare its interface, methods in the public interface should be explicitly identified as such. Right? Be more about what than how. Have names that you can anticipate and that will not change, and take a hash as an options parameter. So then talking about private interfaces, they say be just as intentional with the private interface. Make it as inescapably obvious. Tests because the service documentation can support this endeavor. It talks a little bit about the private keyword, which most people know. But the private keyword denotes the least stable kind of method and provides the most restricted visibility. Private methods must be called with an implicit receiver, or inversely, may never be called with an explicit receiver. And she goes on to talk a little bit about honoring the interfaces of others. So this is when working with other code, right? Do your best to interact with the other classes using only their public interfaces. Assume that the authors of these classes were just as intentional as you are now, and they are trying desperately across time and space to communicate which methods are dependable. The public/private distinctions they made are intended to help you, and it's best to heed them. So pretty much just to sort of give trust into other developers, right? And try to follow, when you can, the public and private distinctions. Then she goes on to the law of Demeter. I saw this image. I thought it was sort of funny. My object never talks to strangers. So pretty much it's a set of coding rules that results in loosely coupled objects. Loose coupling is nearly always a virtue, but is just one component of design and must be balanced against competing needs. Some Demeter violations are harmless, but others expose a failure to correctly identify and define public interfaces. So then we have this example of defining Demeter, right? So Demeter restricts the set of objects to which a method may send messages. It prohibits routing a message to a third object via a second object of a different type. It's often paraphrased as only talk to your immediate neighbors or use only one dot. Imagine that a trips depart method contains each of the following lines of code. So customer.bicycle.wheel, customer.bicycle.wheel, customer.bicycle.wheel.rotate, hash.keys.sort.join. These long method chains are problematic because they tie your object to specific public methods of several other objects. This increases the chances that your object may need to change because of a change in a distant object. But it's a law in the sense of a guideline. It's not always a hard and fast rule. So, there's a section on balancing the likelihood of cost. Balance the likelihood and cost of change against the cost of removing the violation. So I guess it's sort of just like that with anything, right? But in general, you always want to be trying to, if it's working and it's gonna take way more time to change something, right? It's not always something that you'd have to change. But when talking about avoiding violations, one common way to remove these kinds of violations are called train wrecks from code is to use delegation to avoid the dots. In object-oriented terms, to delegate a message means to pass it on to another object, often via a wrapper method. The wrapper method encapsulates or hides knowledge that would otherwise be embodied in the message chain. So to go back a little bit to our bicycle, customer.bicycle.wheel.tire, or .rotate. The problem with an example like that is that they show code like that the customer knows too much about how other code works, and it's a manifestation of tight coupling. So when we see things like that, these kinds of violations, they're clues that that there's objects whose public interface is lacking. Meaning that, you know, that if the object was written with a better public interface, that it's possible that you wouldn't have things like customer.bicycle.wheel.rotate, because there would be a better way to communicate that through a message. I think that might be all of my slides. Yeah, I think that's back at the beginning. Obviously, this is just a big general overview, so I want to keep it short so we could have time for any sort of talk and discussion about it. So anyone has questions or anything?
Yeah, well, if I talk about the dots, she does talk about that last one, the hash key sort join. Looks like it might be bad because of the number of dots, but that's a very typical functional type construct,
yeah,
where the first 3 dots return all the same type. So you're just chaining, and that's a very common kind of relation. She goes, well, this seems like it, but it's actually okay because they all return. Like you could add some more dots or remove some dots as long as they all return enumerable.
Right.
That's a very typical function. It's a lot of filter things are made of that way. Or there's tons of, what's the pattern? This is proxy or something. It's like when you do I/O in Java, you have all these I/Os and I/Os. You do like file I/O wraps buffered, input I/O wraps encrypted, blah, blah, I/O wraps something. So that's done in the constructor, but the dot, it's a very functional sort of thing. You'll see a lot of that in JavaScript, and when it's doing it functionally, it's actually the right way to do it.
Right.
Or at least the accepted way. The right way is the wrong thing. But on that note, we should go to the code and her use case, because I think the story of code and how we come up with stuff is worth examining with the details. And then it's kind of interesting that we did all the principles up front, so we could actually maybe look at the principles while going through the code the first time.
Okay, cool. So there's not a lot of actual code, and are you talking just about the Demeter?
Yeah, it's less about code, but she talks about the bicycle trip thing.
Yeah. Okay.
And more about, I guess there's less code and there's more arrows and messages that match the use case. And I think that's the lesson worth learning. Like, okay, I'm starting from scratch. I have a use case. I start to evolve some objects based kind of on what messages I need to have. And I think that's the exercise that's probably worth following.
So I will share my screen for, I think, the book as well. Okay.
So if we go to the part, like an example, bicycle touring company. So the first couple of paragraphs are what the story is and what our first use case will be. Then she gets into constructing an intention. Then I think she goes off and digresses real quickly into what sequence diagrams are. We can just assume everyone can read what that is without, I mean, I think we can go right to the sequence diagrams.
Right, so this one is she's showing a sequence diagram, right? So diagram.
We'll probably quickly summarize what the problem is.
Oh, okay, right, sorry. So, we have a bicycle touring company. So they have no automation, and currently each trip they offer follows a specific route and may occur several times during the year. They have a bunch of some limitations on number of customers who may go and require a specific number of guides that also are mechanics, right? So customers can pretty much rent their own bikes or bring their own, or sorry, rent bikes or bring their own, and they have they also have bicycle rentals from some bike shops. So
I find that next section, the bullet that I find the most interesting is when she says, "Oh, the reason test first what's the word there? Test first gurus can easily start writing tests because they have so much design experience." And I go, "Oh, that strikes me now why a lot of people learning TDD the first time, it's so hard. And why guys like Kent Beck, who largely invented 3/4 of the things that you should be doing, find it so easy. Oh, well, he's already a design guru, so it's easy for him to figure out what he should do. But even though if you read his books, he talks about thinking, well, what do I need? Well, I think I need one of these. So he reasons things out. If you read his writings fairly clearly.
Right.
But I just find this interesting because we're getting into the, okay, I got a problem. Now, where do I start? Now, if you do the test first thing, well, you should write a test first. A lot of times you don't know what that test should be. And a little bit, not that it gives you the answer, but she says, oh, the reason test first gurus can, she's making you feel better. If you're not a test first guru and you're trying to learn TDD, this is why it's so easy for some people.
Right. And I'm sorry, that was in this part you're talking about, the construction.
Third paragraph down from constructing intention. Then later she goes, well, whether or not you have some ideas of this, and then paragraph there, she goes nouns versus behavior, or classes are nouns, and have data and behavior, and so domain objects are easy to find, but not center, blah blah.
Right.
And then, yeah, so you can probably skip over the UML. UML is there in my mind, and I think in Uncle Bob's mind, the two most useful ones are sequence and class diagrams. There's a whole bunch of other ones. It was required to use some at some companies, and then kind of use case diagrams may be a little useful. All right, now I can go to Mo. You know the problem. We got bikes.
So you're talking. So yeah. So this shows. Do you want me to go through the sequence?
Yeah. So 4.3 now is.
Yeah. So this diagram is representing an attempt to implement the use case above. It shows Mo, a customer in the trip class, where Mo sends the suitable trips message to trip and gets back a response. So here's Mo customer sends a message, suitable trips to the trip class, and gets the message back.
And you can see that the message there, she anticipated the parameters were the dates, how difficult it was, and whether you need a bike.
And yeah, and then you need a bike. So she talks a little bit about how drawing a sequence diagram like this should just pretty much, it should expose what messages are passing, right, between each class. So in this case, customer and trip, yeah, and trip, what's it called? And this is also where she highlights that you don't send messages because you have objects. You have objects because you send messages. So yeah, right. So it goes on from the messaging passing point of view, it's perfectly reasonable for a customer to send suitable trips messages. The problem isn't that customer should not send it. The problem is that trip should not receive it. So now that we have the suitable trips message in mind, but no place to send it, we have to construct some alternatives. So talks about how sequence diagrams help in being able to see, sort of hash out how to do that. Looking at 4.4, right? So we say if the trip class should not be figuring out if bicycles are available for a trip, perhaps there's a bicycle class that should. Trip can be responsible for suitable trips and bicycle for suitable bicycle. Mo can get the answer he needs if he talks to both of them. The sequence diagram looks like figure 4.4, right? So that's here. So Mo customer sending, Mo is sending a suitable trip with on date and difficulty. And then that goes to trip, right, which then sends for suitable bicycle, which talks about trip date and route type. If we see this figure 4.4 for the breakdown here, we know he knows that he being Mo customer that he wants a list of trips. That there's an object that implements suitable trips message. Part of finding a suitable trip means finding a suitable bicycle, and that there's another object that implements the suitable bicycle message. So talks about how, though 4.4 is better, it's also bad in some ways, right? So the design removes extraneous responsibilities from trip, but unfortunately, it merely transfers them to customer. So the problem is that Mo not only knows what he wants, but he also knows how other objects should collaborate to provide it. The customer class has become the owner of the application rules that assess trip suitability. So when Mo knows how to decide if a trip is suitable, he isn't ordering off a menu. He's going to the kitchen and cooking, which is sort of what we were talking about earlier.
He leads into the law of Demeter. Mo knows too much.
Yes, right. Yeah. So Mo knows too much, and there hasn't been a good public interface for him to use, right? That brings up the asking for what instead of telling how. And it takes us to 4.5. And so in this problem, a trip is about to depart and needs to make sure all the bicycles scheduled to be used are in good shape. The use case for this trip, for this requirement, is a trip, in order to start, needs to ensure that all the bicycles are mechanically sound. Trip could know exactly how to make a bike ready for a trip and could ask a mechanic to do each of these things. So if we take a look here, in 4.5, the public method for trip includes the method bicycles. The public interface for mechanic includes clean bicycle, pump tires, lube chain, and check brakes. Trip expects to be holding onto an object that can respond to clean bicycles, pump tires, lube chain, and check brakes. So in this design, Trip knows a lot of details about what the mechanic does. Because Trip contains this knowledge and uses it to direct mechanic, Trip must change if mechanic adds new procedures to the bike preparation process. So they go in saying if mechanic were to implement a method to check the bike repair kit as part of the trip preparation, Trip must change to invoke this new method. So then we get an alternative down here in 4.6, where Trip asks mechanic to prepare each bicycle, leaving implementation details to mechanic. So this one, the public interface for Trip includes method bicycles. The public interface for mechanic includes method prepare bicycle, and Trip expects to be holding onto an object that can respond to prepare bicycle. So now Trip has given up a lot of its responsibility to mechanic. Trip knows that it wants each of its bicycles to be prepared and trusts the mechanic to accomplish this task. Because the responsibility for knowing has how has ceded to mechanic, trip will always get the correct behavior regardless of future improvements to mechanic. So now we don't have to worry since trip is just trusting mechanic to give it the correct info, we don't have to worry about having to change trip if mechanic gets a new set of procedures. Let's see what else is worth highlighting. So now if there's still some issues though, right, with this in 4.6, right, and that's if we were to seek context independence, right, the things that trip knows about other objects make up its context. So gives the example, trip has a single responsibility but expects a context. And 4.6, trip expects to be holding onto a mechanic object that can respond to the prepare bicycle message. Context is a code that trip wears everywhere. Any use of trip, be it for testing or otherwise, requires that context be established. Preparing a trip always requires preparing bicycles, and is doing so, trip always sends the prepare bicycle message to its mechanic. Sorry. You cannot reuse trip unless you provide a mechanic-like object that can respond to this message. The context that an object expects has a direct effect on how difficult it is to reuse. So objects that have simple context are easy to use and easy to test. They expect few things from their surroundings. Objects that have complicated context are hard to use and hard to test. They require complicated setup before they can do anything. So so we were talking a little bit last chapter, right, about dependency injection. The new problem here for trip to invoke the correct behavior from mechanic without knowing what mechanic does, right? So trip wants to collaborate with mechanic while maintaining context independence. At first glance, saying this seems impossible. The solution, though, to this problem is that the distinction between the what and how, and arriving at a solution requires concentrating on what trip wants. So what trip wants is to be prepared, as in they want each bike to be prepared before they make a trip, and bicycles need to be prepared may belong to the province of mechanic. The need for bicycle preparation is more how a trip gets prepared than what a trip wants. So then we go on to 4.7, which is an alternative sequence for trip preparation. So trip prepare trip and it sends itself. Mechanic responds with bicycle.
So you're passing yourself, and then the mechanic pulls bicycle off of the trip.
Right.
And then loops through. So we moved the loop into mechanic from trip.
Right.
And I was thinking, ideally, if these were people, let's say instead of trip, a trip manager, the divvy of jobs in object is like the equivalent of good managers, where good managers delegate. Because you can imagine the trip managers that go, here's bike one. Okay, thank you. Here's bike two. Here's bike three. They don't. They say, mechanic, get those bikes and fix them, right?
Right.
So I tell you, or I ask you to please fix these bikes instead of fix bike one, fix bike two, fix bike three. Now, if you had a bad trip manager who has to micromanage everything, then you might code it that, you know what I'm saying, that way, but you wouldn't. So you push it over to mechanic, fix these bikes. And then where you're future-proofed is, let's say a bike can't be fixed. Well, you don't want the trip to say, oh, well, we got to exclude this bike because it can't be fixed. You want the mechanic to come back, oh, the 5 bikes you gave me, only 3 are serviceable. Which is how you want to do that in reality. You don't want the trip manager to come down in the mechanic shop and say, hey, I don't think this one's working. We're not going to take this one. Right? I gave you 5 bikes, and the bike mechanic comes back and says, here, I can only service 3 for them. So there's only 3 available. The trip manager should only care that, oh, okay, well, I'm going to tell the customer we have 3 bytes. Not worry about the details. Well, I went through all 5 of the bytes. I determined these 3 can't be used. Okay, go ahead.
So I think one of the big themes in this chapter and this section in particular, right, is the idea of trusting other objects. Talks a little bit about how in 4.5 it's pretty procedural, right? Trip's context is large and mechanics public interface. These 2 classes are not islands with bridges between them. They are instead a single woven cloth, right? 4.6 is more object-oriented. The objects communicate in some well-defined ways, at least a few of them, and they are less coupled. But then 4.7 is far more object-oriented. Reason being is Trip doesn't know or care that it has a mechanic, and it doesn't have any idea of what a mechanic does. It just holds onto an object that will send prepare Trip and trust the receiver. So, since the objects were able to have more trust in between each other, it made it so they were able to be more separated and didn't have to worry so much about what each other were doing, which made them less coupled.
We're hitting 11, and if there's any discussion, we should probably do it. It looks like there's only like a page and a half more of this lesson. We could probably delay that to next session. And any comments, questions on this? I think that's a good break. Right before we jump to the use messages to discover objects, I think there could be some interesting discussion there. So as moderator, I'll say it's 11:01. Any comments, questions, insights? Of course, everyone's muted, so if anyone's talking, I have no idea. Just like our normal meeting that takes silence as compliance. So, okay, if there's no other comments, then we'll wrap for this session. Alex can wrap up that last, use message, discover objects, creating a message-based application. So I think that those are the biggest lessons from this code. And then we need a volunteer for chapter 5. Who shall go? And in the absence of volunteers, I can always pick them. Diego, Alex, and I and Andrew have gone, so I would say Don, Brett, Sam, or Scott.
Yeah, I'll do it.
Okay. Don will pick up chapter 5. If there's any parting comments we want, we should have them. Otherwise, we'll resolve, and any possible remote viewers can go back with the 11 o'clock times. Or whatever time zone you're in. Okay, I hear nothing. So thank you for coming to Nested Loop, and we'll see you in 2 weeks.
Thank you.
Thank you. Good job. Good job, A Brothers.
Good job, Alex.
Good job. I like the slides. Hope you remember that. All right, cool. See you in 2 weeks.